Okay, hi everyone. Just give me a second to share my screen. Can everyone see okay?
Yeah.
So today I'm going to be talking about the thermodynamics of binding. So before I go into the more quantitative stuff, I just want to go over why it is that we study the thermodynamics of binding. In biology, by far the most important interactions are non-covalent interactions. So the interactions between the two strands of DNA, protein recognition of DNA, enzyme substrate recognition, or hormone receptor binding, all these things are governed by non-covalent interactions because they're strong enough for biological function, but weak enough that there's an equilibrium between bound and unbound protein or DNA or whatever it is you're studying. So by understanding the thermodynamics of these reactions, we can understand how strong these interactions are, how specific these interactions are, and how cells use them to regulate different phenomena, or how, for example, to design drugs that target specific proteins. So let's just take, for example, a very simple, just single protein and simple ligand. We can model it in general with, in this form. So you have a protein and a ligand form a protein-ligand complex. And the small black circle denotes that this is a non-covalent interaction. And as usual, for all these types of equilibria, we can write an equilibrium constant for this reaction. If we read it from left to right in this direction, so free protein, free ligand forms a protein-ligand complex, then the equilibrium constant is known as the association constant, where the protein-ligand complex concentration is on top and the free protein and ligand is on the bottom. And then this we can just convert into a standard free energy change for the binding reaction, which as usual is just negative RT, natural logarithm of your equilibrium constant. And then, so this delta G is a measure of the affinity of this interaction. So it's a standard free energy change of ligand binding when 1 mole of ligand binds 1 mole of protein under standard conditions being the protein and the ligand are 1 molar concentration. So if your delta G is very low, that means that the formation of this protein ligand complex is favorable, which means that your protein has a high affinity for your ligand and wants to bind ligand. You can think of it that way. And then, of course, we can also write the equation in the reverse. So here we modeled it as a free protein and free ligand combined to form a protein-ligand complex. We could have just as easily written it in the reverse direction. So you have first a protein-ligand complex with their non-covalent interaction, and they dissociate to form a free protein and free ligand. And the expression for that would be the inverse of your association constant with your free protein and free ligand in the numerator of your dissociation constant. And we can also write a standard free energy change expression using the dissociation constant. And note, since that the dissociation constant is the inverse of the association constant, the delta G expression is doesn't have a negative in front, it's positive because the natural logarithm of an exponent is the exponent times the natural logarithm. So we just bring, you can imagine that the associated constant is Ka raised to the -1, you bring out the -1, and the negative here becomes positive. So in the textbook, you see that both KD and KA. So why is it that later on in textbook that we tend to use KD? The reason we use KD instead of the association constant, and not because they're fundamentally different, they're interconvertible. If you have Ka, I can give you a KD. If you have KD, I can easily give you the Ka. They're just inverses of each other. But the reason we choose to use a dissociation constant is because the dissociation constant is the ligand concentration at which half of the total proteins are bound with ligand. And this is, in other words, the fractional occupancy is 0.5. And I will go into the fractional occupancy in a couple of slides, but I just wanted to bring that up right here. So that there is a reason why we use KD instead of Ka, but it's a matter of convenience, not because that there's a fundamental difference between KD and Ka. And here I just wanted to bring up a table of common KD and delta G binding values, just so that you have a an idea of what they look like in biological settings. So for example, if you have an enzyme ATP interaction, so a lot of enzymes are ATP dependent, you might have millimolar to micromolar affinity. So your KD is 10 to the minus 3, 10 to the minus 6, but you can get somewhere as strong as 10 to the minus 15 for some interactions. I think the interesting thing here is to note how your standard free energy change of binding changes with your dissociation constant. So if you go from 10 to the minus 3, 10 minus 6, you get a delta G standard free energy change of around 17 to 18 kilojoules per mole. And you see this is consistent throughout at 300 degrees Kelvin. So if you go from micromolar affinity to nanomolar affinity, that's 3 orders of magnitude, you get another 17 kilojoules per mole of extra affinity. You go from nanomolar to picomolar, you get another 17. And again, when you have 3 orders of magnitude from picomolar to femtomolar, you get another 17 kilojoules per mole of affinity. So as a general rule of thumb, at 300 degrees Kelvin, every order of magnitude that KD decreases, you decrease your standard free energy change of binding by 6 kilojoules per mole. So by decrease, you mean the affinity is stronger. So decreasing KD, again, means that the affinity is of the protein for the ligand is stronger. So before I mentioned fractional occupancy in relation to the idea of why we use KD over Ka, right? I'll remind you that KD is the concentration of ligand at which half the protein is bound with ligand, and that's known fractional occupancy 0.5. So going back to the idea of fractional occupancy in general, or fractional saturation, is the fraction of protein that is bound with ligand, or for example, the fraction of DNA sequence bound with protein. It doesn't really matter, it's just a fraction of one species bound by another species. And we can represent fractional occupancy F using this expression. So at the top is the concentration of the protein ligand complex. So that's your bound protein. And then in the denominator, we just have total protein, right? And total protein is just the sum of free protein and then bound protein. So that is your fractional occupancy. And then we want to convert fractional occupancy to a more usable form, right? Because we don't really have access to this protein ligand complex value. So we know ligand concentration experimentally, we put in the ligand. So we want to convert this into a more usable form. So in order to do that, we replace this protein ligand complex concentration value with this expression using the KD expression. So remember, KD is the free protein concentration times free ligand concentration divided by the protein ligand complex concentration. So you rearrange that and you get this expression, and then you plug back in. And then here you just, if you multiply by KD top and bottom, you get this expression and a little bit of mathematical massaging, and then you get this nice expression. So then your fractional occupancy, again, the fraction of total protein that is bound with ligand is purely a function of the ligand concentration and the dissociation constant. And then the special thing to note about this fractional occupancy is what happens to ligand concentration when the ligand concentration is equal to the dissociation constant, right? So if we plug in KD for the concentration of ligand, we get KD over 2 KD, which means that fractional occupancy is 1/2 or 0.5. So this is what I was saying before. KD represents the concentration of ligand at which the protein or species of interest is half bound. And then I'll remind you that KD is defined at a specific temperature, right? As you change the temperature, you get a different equilibrium. So a particular KD is defined only for a specific temperature. So when we make a plot of fractional occupancy as a function of ligand concentration, we have to make sure that that's done at a constant temperature. We can't change temperatures as we conduct this plot, as we change the value of the ligand concentration. And then you'll note, so when we start off with no ligand, well, obviously there's going to be no protein bound with ligand because there's no ligand available. As we increase ligand concentration, the protein readily binds the ligand. When we get to the special value at which the ligand concentration is equal to KD, we get fractional occupancy of 0.5. And as we increase ligand concentration, let's say towards infinity, you plateau at fractional occupancy as 1 because the amount of protein bound is limited by the total number of protein you have in the first place. You cannot bind more protein than the total protein available. So that's why you have this plateau behavior. So how is it that we determine KD? So before, the way we came about fractional occupancy, we derived it using KD. But in practice, we use fractional occupancy to determine KD, not the other way around. So in order to determine KD, what you need to do is perform a binding assay, right? So a binding assay is some experimental procedure whereby you can separate free protein and, free ligand and bound protein. If you can do that, you can determine KD. So in this particular example, which is in your textbook, you can find the KD of estrogen, which is a hormone, for the estrogen receptor. And then, so you have free estrogen, and then you have a radio-labeled version of estrogen of known concentration mixed in with your non-radio-labeled estrogen. And you know it's given to you that the radio labeling of estrogen does not impact the binding of estrogen for the estrogen receptor. So therefore, you know that the radioactivity present in the bound protein is proportional to the amount of ligand bound to that protein. So then you can mix these together, you get the binding of the ligand of the radio-labeled estrogen to the estrogen receptor, you centrifuge to separate the protein from the free ligand. And then based on the radioactivity left at the end, you can determine the amount of ligand bound, which is equal to the amount of protein bound. And that's how you determine that protein ligand complex concentration. And then if you do that multiple times for different ligand concentrations, you again generate this plot. So then now we have the experimental determination of the fractional occupancy volumes, fractional occupancy values. And from that, we can determine KD. So we know that KD is the ligand concentration at which fractional occupancy is 0.5. So this red line right here is where fractional occupancy is at half. And then we go down. So we know that for this particular value of ligand concentration is the KD. KD happens to be 5 × 10⁻⁹. So that's how we experimentally determine KD. And that's all I have. If anyone does anyone have any questions? I think I'm 2 minutes early. But if not, you can just private message me and I can answer those questions too.
Okay, I'll be continuing some of that, more on the graphing side. Let's see. Okay, can everyone see? Okay, so to kind of recap some of what Tintin said, so we have this basic model, and kind of what we're doing before we get more complicated with allosteric interactions and competitive binding is we just have one protein that can bind one ligand and vice versa. The ligand only binds to the protein and there's no allosteric interactions, and the protein only binds one unit of the ligand. So as you saw before, KD is equal to this expression. P is the unbound protein, L is the unbound ligand, and P dot L is the bound complex. And then you can define the fraction. And something to note is the concentration of P dot L plus the concentration of P is a constant, because those are the only two states that the protein can be in, and the protein doesn't disappear or have more appear. It's just what you added initially for the remainder. So kind of to go over again, I'll talk about kind of the behavior of this graph. So there's multiple ways that you can mathematically state it, and our independent variable is L. And what we really care about is what L is relative to KD. So when L is much greater than KD, your F becomes about L over L, which is 1. So as the ligand concentration becomes, free ligand concentration becomes very high, you essentially can saturate all the receptors, and that's kind of like Le Chatelier's principle. And when L is very small, you get kind of a linear growth at the very close to 0. And then when L is, of course, equal to KD, you get that is the protein is half bound. So there's other ways that you can actually graph this. So I'll go over some of the ones that you saw in lecture. So in this second graph, you see a log-log plot. And on the y-axis, you have 1 over f. So I'll kind of go step by step into kind of hinting at what this actually represents. So since f is the fraction bound, 1 minus f is essentially the fraction unbound, because in this simple system, it's either bound or unbound. So just due to complementarity, or you can also just kind of mathematically reason it out. So f over 1 minus f, if you do the math, it's essentially the ratio of bound to unbound protein once you simplify. So if this ratio is less than 1, it means there's no more unbound than bound. If it's equal to 1, there's an equal amount, which you can also think of as when L equals KD. And then if the ratio is greater than 1, there's more bound than unbound. So that kind of takes us a little past the first step. So now talking about what the logarithm means, because some people can get kind of freaked out. So essentially, a logarithm is just a function that kind of maps values to other values. So if if the fraction, your f over 1 minus f is less than 1, it becomes a negative number. If f over 1 minus f is 1, then the log of it is 0. And then if it's greater than 1, then the log will be positive. As you can kind of see in this graph, you have 0, negatives, and positive numbers. So again, you still have kind of the same regions as you see in the non-log plot. They're just kind of distorted, but it's showing you really the same thing. So now kind of to further interpret it, when f equals 0.5, that's when your log is 0. And when on the top graph, when you're to the left of that point, that's really like the negative y values on the log plot. And then to the right on the top graph is the positive y values on the bottom graph. So why would you want to do that? Well, linear functions and determining coefficients and stuff is very easy and commonplace with linear plots, whereas working with like a hyperbolic function, it's kind of harder to work with. But they're really showing you just the same thing. So now we have this other sort of plot where we talk about changes in f with respect to changes in the magnitude. So again, this x value is L over KD, and kind of rewriting f in terms of that L over KD, you have L over KD plus 1 plus L over KD, and you have logarithmic scaling. So if you note, it goes like 1, 10, 100, and there's equal spaces between 1 and 10 as there is 10 to 100. So as you can kind of see, the slope of f with respect to your x value is not a constant. So that can be kind of difficult to calculate or difficult to state exact changes, but you can calculate it pretty easily. So it's essentially x over 1 plus x, where x is this ratio. So if you have L equals KD, then your fraction bound is essentially 1 divided by 1 plus 1, or 50%. Whereas if your ratio is 10, then the fraction bound is 10 divided by 1 plus 10, which is roughly 90%. And then, so it's pretty easy to calculate. And now going on to the Van Hoff equation, which can tell us things about the thermodynamic properties. So kind of the general equation, delta G naught equals delta H naught minus T delta S naught. So kind of as you saw earlier, you can write the delta G of binding in terms of plus RT ln KD. The plus is because it's the dissociation constant, and we're talking about the delta G of binding. So it's the reverse reaction on one side. So you can kind of restate this as RT ln KD equals delta H naught minus T delta S. And then if you divide by RT, you get this kind of weird looking equation, but it's actually something you can plot as a line. If you have your X being inverse T, and then your Y value is ln of KD. So you can actually determine by doing the previously mentioned experiments like with estrogen at different temperatures and then finding the KD values. And if you plot it in this way, you can tell what your delta H is based on the slope, and you can find out what your delta S is based on the intercept. So kind of a final thing is just keep in mind, if you look it up online, you might see a negative sign, and that's because, as I said earlier, we're having the reverse reaction on one side. So now for kind of conceptually understanding the results. So the Van Hoff equation is very general for all of chemistry. It's not just this ligand binding. So your delta H naught and your delta S values in general in chemistry could be either positive or negative, but we're looking at a very specific subset of reactions. So those will tend to have certain characteristics. So binding of receptors tends to be enthalpically favorable or negative delta H of binding. But your delta S naught is a bit more interesting in that it could kind of be either side, positive or negative. And this may seem kind of weird because you think, okay, a free ligand binding to a receptor, that's two things going into one. So therefore entropy should be negative. But that only is part of the story. You have to think in terms of, yes, you do have this translational and rotational degrees of freedom loss. And you also have often conformational changes and restrictions when bound, but there's also the entropy of the solvent. So this is kind of analogous to the hydrophobic effect when you're talking about protein folding in the very start of the class. So it's hard to know kind of a priori whether all these things will sum up to positive or negative. And it actually kind of depends on what type of mechanism. So experimentally, like lock and key type binding, which you saw in your intro bio classes, is thought to actually be largely entropically driven due to the solvent energy having a very positive delta S naught, which kind of outweighs the loss of entropy in the ligand and protein. So that's all I have. So I believe, so I will stop sharing.
All right. Hey, everyone. So I will be picking things up and we'll talk about binding curves and how they relate to cooperativity. And you know, there are different types of binding curves, and our best example, I think, is looking at the oxygen binding proteins, myoglobin and hemoglobin. So you can see on this graph on the right, there are definitely differences in how myoglobin and hemoglobin are binding oxygen, depending on how much oxygen is actually present. And the x-axis for measuring in milligrams of mercury of oxygen, partial pressures of oxygen. So for myoglobin at low partial pressures, we still have a relatively high amount of O2 bound to myoglobin, around 80%, this low partial pressures. And as you increase, that slowly increases up to almost 100%. Hemoglobin, on the other hand, at these low partial pressures, we have relatively low amounts of oxygen bound, around 20%. And as you're increasing, it suddenly you can get all the way up to where myoglobin is at these higher pressures, around 100%. So we'll say like at these low partial pressures, that's the partial pressure of oxygen in the tissues. And at the higher range up here, maybe between 60 and 90, that's the partial pressure you'd find in your lungs. So what is this allowing? Well, or what's the point of this? This important thing to note is that for hemoglobin, which is we'll say it's the purple curve here, that it has an ultrasensitive response, meaning it has a really large change in the amount of oxygen bound to it over a rather small change in the concentration of oxygen present. So on this graph, it is the inner two purple lines that are designating where at this let's say 0.5 log, negative 0.5, you have relatively low amount of O2 bound, and just going to positive 0.5 log, you have almost 100% oxygen bound. So that's what we call the ultrasensitive response that will apply to hemoglobin. Now for myoglobin in blue, I have the graded response, which is a little slower. You can think of it that way. We have the same amount of change. To get the same amount of change as the hemoglobin curve, we have to change the concentration of oxygen a lot more. That's designated by these lighter, I guess, green colored lines. So in terms of hemoglobin, that allows hemoglobin in the lungs where there's a lot of oxygen present. It allows it to pick up a lot of oxygen. It'll be highly saturated. But by the time it gets to the tissues where there's low oxygen concentration down here, it won't bind it as much, and it'll be able to unload that oxygen to give to the tissues. So hemoglobin we think of as an oxygen transport protein. Compare that to myoglobin, we think of that as a storage protein, because overall, as you saw in the previous graph, has a relatively high amount of oxygen bound over a large concentration of oxygen, meaning it's better at storage, just holding oxygen for a time when the body or cells need it. So the thing that causes this ultrasensitive curve is cooperativity, which is when you have, let's say in a protein or at some active site, when you get one substrate bound, that'll change the binding strength or the affinity of the other active sites present on that same protein. And there are two types of cooperativity, positive and negative. We'll talk a little more about that at the end of these slides, but for the next couple of slides, I'm going to be talking about this mostly in the context of positive cooperativity. So you're getting a change in affinity as more substrate gets bound. And one thing to draw a distinction between is cooperativity and allostery. So allostery is where you have a molecule binding at a different site other than the active site, and that can affect the active site in some way, usually through a conformational change. So you absolutely can have allosteric cooperativity. So that's shown in this left example here, where you have one substrate binding to one of the active sites, and that'll stabilize the other active sites, thereby increasing its affinity for substrate. But you can also have non-allosteric cooperativity. This is an example from your slides looking at DNA with two binding sites here. So the transcription factor will come in and bind. And there may not be something like a conformational change that'll affect the binding site itself on the DNA, but the presence of this first protein already bound can help draw in and bind the second protein. So that'll increase its affinity in that sense. So you'll still have cooperativity, just not through any allostery. So make sure you draw the distinction between those two concepts. So for cooperativity, we designate two different states for our enzyme, which we normally talk about when we talk about these concepts. So we have the T state, stands for tense state, and we have the R state, it's a relaxed state. In the tense state, you usually find the enzyme is in the tense state at a low ligand concentration. We'll say that has a K dissociation constant, KD1. In tense state, usually it will have the lowest affinity for your substrate, whatever that may be. And then once you have one substrate bound, the enzyme will transition into the R state. Again, this is an allosteric model. So now, once you have one bound through allostery, the other active site present now has a higher affinity for the substrate. And if it has a higher affinity, that means the dissociation constant has now decreased. So let's say for the other active site, that would be KD2. KD2 has to be lower than KD1 if we're going to get this positive cooperativity. That way you'll have the increase in affinity. So we can actually plot these out on the fractional saturate occupancy versus ligand concentration curve. So our R states in red, T states in blue, and they take on curves, hyperbolic binding curves. So you have the R state, of course, it's going to be above the T state because it has a higher affinity. And if we're showing the actual fractional occupancy curve for our enzyme accounting for cooperativity, that's shown in green, and it'll have a sigmoidal shape. So make sure you know the differences between hyperbolic and sigmoidal curves. That's a common question that gets asked on the tests. So there we go. Oh, I think I jumped there. So I like to think of this as, the actual binding curve, which is shown by the purple line here, is a mix of the T and R state curves, kind of like an average. At low concentrations, you'll mostly have the 10 state present, so it'll basically follow this 10 state curve. And as more and more substrate is bound, more and more of your enzymes are switching over to the R state. And that's going to increase fractional saturation. And eventually you'll start matching the R state binding curve towards the top. That'll give you your sigmoidal curve. And over on the right here is our equations that John and Tintin talked about. So for fractional occupancy, we can say it's ligand concentration divided by the KD plus concentration again. And I think a more common form you'll see, or at least in this class, is we'll change it and put it in terms of ligand concentration divided by KD. And overall, as you're getting more saturation, this term ligand concentration over KD is increasing. So one way we can quantify cooperativity is through the Hill coefficient. So we'll look at a plot such as this on the right. We're plotting our concentration on the x-axis over log concentration over a log against log of our fractional saturation in terms of fractional saturation divided by F divided by 1 minus F. So that gives us linear lines, which makes things a lot easier to understand. And the Hill coefficient is the slope at this point in the center where you have your protein half saturated. So we define that as this term as equal to 0. This is equal to 0. This inner F divided by 1 minus F has to equal to 1. So your fractional saturation is at 0.5. So basically, what is the slope at this point? What is the slope at the KD value? And your Hill coefficient will increase as the differences between your affinities increases. So we have our R state curve and our T state curve here. Where it crosses the x-axis is your KD value. So you can see the T state, we have the higher KD, R state, lower KD, that's expected R state, has a higher affinity. So the bigger difference between these, the greater the slope will be, the greater the Hill coefficient will be. So our equation for calculating that coefficient is given here, 2 divided by 1 plus the square root of our KD2 divided by KD1. So to derive this equation, we can plot our fractional occupancy shown here. And I'm not going to go through the derivation right now, but you can see that we have to account for both KD values, right? That makes sense. If we're having our enzyme switch from one KD to another KD, and we get that sigmoidal curve, we need to account for it when we're talking about our binding curve. So now, depending on how many active sites you have on your protein, on your enzyme, you're going to have to account for it in this fractional occupancy measure. And therefore, that's going to affect this numerator up here and also denominator. So basically, depending on the number of binding sites that you have in your protein, that'll be the upper limit of your Hill coefficient. I don't think in this class you'll ever be asked to do any problems other than with this equation where you assume this numerator is 2. But that's just a common question that gets asked as well. The upper limit is the number of binding sites or subunits you have. And if your KDs are equal, both KD2 and KD1 are equal, this will become 1, and your whole Hill coefficient will become equal to 1. That means there's no cooperativity happening there, and you'll get your regular graded response curve. So now let's talk about positive versus negative cooperativity. We're back on these log versus log plots. So on the left is positive, on the right is negative. And just make sure you know how to identify differences between these two. For positive, we have an increase in affinity, right? So as you can see from the green curve, we're starting on our T state curve, and we're transitioning over to the R state curve. Because we do that, the slope at this point in the center will be positive, or will be greater than 1, because these slopes are going to be 1. Now, the opposite is true for negative cooperativity. Negative cooperativity is when we're having a decrease in our binding rate, basically. So we're, in this case, rather than going from T state to R state, we're actually going from R state to T state. So we're starting from a red line, R state, transitioning over to our lower affinity curve, and that'll give us a slope less than 1. So make sure you know how to identify those two, and when you're working through problems, know if you're dealing with positive or negative cooperativity. So just to summarize, if you're calculating your Hill coefficient and you have a coefficient that's greater than 1, that's going to indicate positive cooperativity, and you're going to get a sigmoidal curve. So on this graph, our graded no cooperativity curve is going to be this red one in the center. So you can see moving up to Hill coefficient of 4, we have a nice sigmoidal curve in black. And for negative cooperativity is when this Hill coefficient is less than 1. So you can see it's this curve has occupancy a lot less than the Hill coefficient when it's equal to 1. And the limit is set by number of binding sites. In this case, the number of binding sites is probably 4. And then important thing to know is that with negative cooperativity, it's not technically it's not going to decrease binding once the KD switches. You can see that overall, as you increase ligand concentration, you're still increasing fractional occupancy. It's just that a better way to think of it is that it's less efficient compared to an enzyme that has no cooperativity. So that's why you have less fractional occupancy at this curve. All right, that's all I have. If you have any questions, just private message me in the chat. Sam, you can go ahead.
All right. Hi, everyone. So I'll be talking about a new topic, but it really builds upon the concepts that we've learned so far about binding and the previous tutors talked about. I'll be talking about Michaelis-Menten kinetics and enzyme inhibition. All right. So what are Michaelis-Menten kinetics? They define, it's a simplified model that defines how enzymes speed up a reaction and convert a substrate into a product. And it breaks the entire process down into 2 steps. The first one of which is a binding event, which is very similar to what the previous tutors talked about. And the second one is the actual catalysis event. Again, it's a very simplified model, and it makes several assumptions. One of which is that the binding event is reversible, as it is denoted by a K1 rate constant and a K-1 rate constant. And the second step, the catalysis, is irreversible and is denoted by the K2 rate constant. And again, another assumption that it makes is that this reaction is happening at steady states, and I'll get more into that later on. But for now, just keep that in mind. And when you look at the plots that plots the initial velocity of the enzyme, or the velocity of the enzyme when the enzyme's unsaturated, so right when it starts beginning to catalyze the reaction, as a function of the substrate concentration, it looks very similar to the plots that we've seen so far with binding. It's very similar to the hyperbolic binding isotherm. And again, I'll get more into that later, but it really shows how intertwined Michaelis-Menten kinetics and binding isotherms are. And another important term is the Vmax, and as the name suggests, it's the maximum velocity of the enzyme when it's fully saturated and is catalyzing the reaction. And finally, the Km, which is very similar to the Kd. It's the Michaelis-Menten constant, and it defines the substrate concentration at which the velocity of the enzyme is 1/2 the Vmax. So now on to deriving the Michaelis-Menten equation. It's quite lengthy, but I'll just go over the key ideas. So we start with the reaction that I talked about before. There's the binding followed by the catalysis, and I said that the reaction is at steady state. So what does that mean? It means that the rates of which at which the enzyme substrate complex, so this intermediate here, is getting deformed is equal to the rate at which it's getting formed. So how do we write this down? Well, there are two ways that it's getting destroyed or like deformed. It's this k minus 1 here and this k2 here. And we set these two equal to the rate at which is being formed. So this k1 here. So over time, the concentration isn't changing, and so the derivative is equal to 0. We rewrite this in terms of the concentration of the enzyme substrate complex, and we get this fraction here. Moving forward, we can say that the initial velocity of the enzyme, the V naught, is equal to K2 times this enzyme substrate complex. It's a simple unimolecular reaction that you guys learned about in the kinetics unit of the course. And since we have this new fraction, we can plug it back into this equation and get this new fraction. So it's this next point is very similar to what John was talking about, how sometimes some concentrations are hard to calculate experimentally. And this concentration of the enzyme, it's the concentration of the free enzyme, and that's hard to calculate. But the initial enzyme concentration, E naught, is known. So we want to rewrite this concentration in terms of our known values. And basically the concentration of the free enzyme is simply the initial concentration of the enzyme minus the enzyme substrate complex. So we get this new equation for our E. And then finally, another assumption is that the substrate is in large excess of the enzyme. And this is pretty reasonable because usually this is the case that the substrate is there's much more substrate than enzyme. So it makes sense that there's not much substrate going to be used relative to the entire concentration. So we can say that the initial concentration of the substrate is equal to the final concentration of the substrate. So now we have these two new equations for substrate and enzyme, and we plug them back into this fraction here. And we get, after some rewriting, it's just some basic algebra, we get this new fraction for the enzyme substrate complex at steady state. And here, notice that we have this Km appears again, and the Km is simply the rate constants at which the enzyme substrate complex is getting deformed over the rate constant at which it's getting formed. But we're not done yet. There's a couple more steps left. If we notice here, we had this equation for V naught, so we can plug this back into here. And then if you go back to the very first slide, I said that there's another term, the V max. And when you think about the V max, it's essentially when this maximum velocity is happening when all the enzyme is bound to the substrate. So how do we put that in terms of mathematical terms? Well, it's simply when the initial concentration of the enzyme is equal to the enzyme substrate complex. That's saying that all the enzyme is bound to the substrate. So we can plug E naught into our equation for V max. And if you notice, K2 times E naught is appearing in both equations. So we can simply substitute back V max into this, and we get our final Michaelis-Menten equation, which relates all the parameters I've been talking about so far, V naught, V max, and Km. And again, Km is the same thing as before. Now moving on, I mentioned this in the very first slide about how it's so similar to the binding isotherm. And so why is that? Well, if you look at the equation for V naught, it should be very familiar. In fact, it's almost identical to the equation for the fraction bound in binding problems. I just rewrote the fraction bound equation here. And if you notice, the formula for V naught is simply this multiplied by the V max. So there's a V max in the numerator, and the KD is the Km. And this really shows why the Michaelis-Menten model, how it's set up, how it's a binding event followed by a catalysis event. And so the V max takes into account the catalytic part of the this model. Another way we can see how similar these two concepts are in the Km and the Kd constants. This is the equation for Km. And when the K2, or the rate of catalysis, is much, much slower than K minus 1, this Km becomes essentially K minus 1 over K1, which is exactly the same as Kd. So again, showing how similar these two events are. And as you notice, look at the graph here. When the substrate is much, much lower than the Km, the initial velocity is exponentially increasing, and the rate is proportional to the amount of S. But when substrate is in excess, the enzyme is fully saturated, and so the rate becomes independent of the substrate concentration, and it kind of plateaus off like the isothermal hyperbolic binding isotherm. And so why is this model useful? Well, we can characterize enzymes based on their catalytic efficiency. So what is the catalytic efficiency? I'm going to explain this concept by using these two extremes. I'm going to first start with when the substrate is in large excess of the Michaelis-Menten constant. This is again the same equation we derived before. And if S is much larger than Km, this fraction becomes extremely small. So we can say this entire thing becomes essentially Vmax, because we can just cross this off. And it turns out that V naught will equal K2 times E naught, which is just the Vmax. And usually we refer to this K2 rate constant as the catalytic rate constant, Kcat, or the turnover number. It turns out that in the simplified Michaelis-Menten model, these two are equal, but in more complex models, they're not equal. But for now, we can just say that K2 equals Kcat. And then we do the same thing for when the substrate is much less than the Km. And we see that this fraction becomes extremely small, and we get this final equation. And since we just said that the Kcat is equal to the K2, this becomes Kcat over Km. And this is referred to as the catalytic efficiency of an enzyme, and it's unique to each enzyme. And we can compare the catalytic efficiencies of two enzymes to see which one's more efficient at catalyzing the reaction. So you can imagine how useful this is. And it has a max value of 10 to the 10 per molar per second. First, notice the units. It's per molar per second, so it makes sense because it's a bimolecular reaction. And second, this should be very familiar because it's the diffusion limited rate constant, and it makes sense that enzymes have a diffusion limited rate constant, at least most of them. It's because most enzymes can't catalyze a reaction faster than the rate at which the substrate is coming into the enzyme, because the enzyme has to first get the substrate and then catalyze. So that's why most enzymes tend to have a maximum value of 10 to the 10 per molar per second for their Kcat over Km. Now I'm going to move on to the final topic, which are the different types of inhibition. But before I go over that, I'm going to talk about Lineweaver-Burke plots. Again, it's very similar to what John was talking about, how to make graphs more visually, pleasing, and to actually obtain these parameters. We invert the Michaelis-Menten equation, and we get this equation, which is essentially a linear equation, y equals mx plus b. And if you plot the reciprocal of the V naught as a function of the reciprocal of the substrate concentration, the slope will simply be Km over Vmax, and the y-intercept will be 1 over the Vmax. And we can obtain the parameters through this plot. Now to different types of inhibition. I'm going to first talk about this one here, covalent, irreversible, non-competitive. I think it's the most intuitive one. It's easiest to understand. It's kind of in a name. It's irreversible. So when the inhibitor binds to the enzyme, it completely knocks it out, and it blocks the substrate binding permanently. So it destroys all functionality. The next three are a bit more involved. I'm going to first talk about competitive inhibitors. And these inhibitors block away from the active site, actually block in the active site in a reversible way. So they kind of compete with the substrate. In this case, the Vmax remains the same, but the Km increases. And this is the equation for the new Km. And as you can see, Km is increasing and the Vmax remains the same in these Lineweaver-Burke plots. And I just want to say conceptually why this is happening. The Km increases because, as you can imagine, if the substrate is competing with the inhibitor, it'll take more substrate to actually reach the 1/2 of the Vmax, because they're binding to the same site. So that's why the Km increases. But if you notice, if the substrate is in large excess, it can kind of outcompete the inhibitor. And that's why when the enzyme is fully saturated, the Vmax remains the same and the enzyme has the same functionality. And if you notice, the Km, this new Km is dependent on the inhibitor concentration and the constant for the inhibitor enzyme complex. Now, the last two types of inhibition, the non-competitive inhibitors, and these bind away from the active site. So you can imagine they'll have different effects on the enzyme. First, I'll talk about reversible non-competitive inhibitors. These decrease the Vmax, but the Km is the same. If you notice here, the Km is the same, but the Vmax decreases, and this is a new Vmax, which again is dependent on the fraction of the enzyme bound to the inhibitor. Again, a conceptual reason of why this is happening, because they're binding away from the active site, the substrate can bind just the way it was binding before without the inhibitor. So that's why the Km, so the binding event is still the same, but these inhibitors are leading to a conformational change at times to the enzyme, which reduces its activity, and that's why the Vmax decreases. And I just want to point out that just notice how when the Vmax is decreasing, the y-intercept goes up, which is kind of counterintuitive, but just notice that we're plotting it as an inverse of the V0. So just take that into account, that the Vmax decreasing is it going up in this graph. And then finally, substrate dependent non-competitive inhibitors. It's in the name. They bind only when the substrate is present. Again, like the reversible non-competitive inhibitors, they decrease the Vmax for the same reason. But in this case, you're also decreasing the Km. And these are the new values for the Km. And you can clearly see this, clearly see it in these Lineweaver-Burke plots. And I just want to point out that the fact that the Km is decreasing is not because the enzyme has more affinity for the substrate, but it has to do with equilibrium. So just keep that in mind, that the enzyme is suddenly not more, doesn't have more affinity for the substrates. And yeah, that's all I have.